Let's look a little more at how types and inference and notation work in Plait. Here I've got a function f that takes an x and a y, and it has an if where it picks either x or y. Right now it's always going to pick x. But the thing you see is that the function f doesn't care what kinds of thing x and y are. It cares that they're the same type because it doesn't think about the evaluation of true here, but I can apply f to 1 and 2, or I can apply f to true and false, and it'll work either way. And that's because the type for f is inferred to be polymorphic. It's for any alpha, 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 arrow, alpha. We have to give it two of the same kinds of things, but it can be any kind of thing. Now in Plait we can also write types down. I could write the alpha literally here. And if I do that, then I'll still get the same result. But I could also write a more specific type. I could write number type here. And if I do that, then I've constrained the types that the inference engine is allowed to consider, and so now f only works on numbers. If I try to pass it true and false now, even though I didn't change the body of the function, the type annotations did affect what type is given to that function f. If I change it back to alpha here, and what if I make it alpha, but I also change it to add 1, right? So at first glance it may look like I'm writing a polymorphic type alpha here, but the body of the function f uses x in a way that it has to be a number, and so it's still inferred to be number, number, arrow, number. In fact, when we write an identifier like quote a here, we're not really making a polymorphic declaration. We're just drawing a question mark and spelling a question mark quote a instead of the question mark as we wrote it in curly. But there is a meaning to using the same quote a in two different places. Let's change this to be a tuple instead. If I change this to values, now I'm not doing if, I'm returning both x and y as a tuple. The type for f is still number, number as the arguments, and now it's number star number as the result. If I take away this quote a, then the type will be different. I will see that the type is number alpha and then number star alpha. That's because we don't have an if here anymore. We're not constraining x and y to be of the same type. And so if I leave off all of the type declarations, that's the same type that will get inferred. So using a quote a is kind of like a question mark. The type inference will still pick something to go with that if it has to. But by using the same name, when I had quote a and quote a, I constrained x and y to have the same type. I could also use quote a arrow quote a here, and now I'm constraining them not to be the same type, but still to be related. And so even if I change this back to x, so it's not a number anymore, and I look at that type, then it says that the first argument has to be an alpha, and the second one has to be alpha arrow alpha for the same alpha. As opposed to if I wrote betas here, this constrains y to be a function, but it doesn't have any connection to what x has to be. They're completely independent. So I can use f on 7 and a function that takes a Boolean and returns it. Or I could do the same thing with number as the function type and Boolean as the value that I pass in first. Right. What happens if I put just quote a here? What type do we get back? So that will constrain the argument type of y to be the same as the type of x, but it still doesn't constrain anything about the result. On the other hand, if I make a list of x and y applied to x, now what happens is that the type inference figures out that the result type of y has to be the same as the type of x for this list to be sensible. So when we look at that, we see all the argument variables involve alphas now again. If I write a completely different function, so let's just change this to f of x, and down here I have g of x of a. That will also return x. You can see that I've used quote a in two different places, but because these are in different definitions, they're unrelated. So the types of f and g both look like the identity function. I can make a tuple where I pass f a number and g a Boolean, and that's just fine, because f and g separately have a polymorphic type, and the printer always just starts over with alpha here. Even if I write beta and I look at the type of g, it's going to print alpha, right, because it just picks the smallest letter that it has available within that type expression. But all of these things at different definition levels are distinct. If I make another change, let's go with just f, but let's have f return a function that takes a y, and let's claim that y is also of quote a. So I have two different functions here, and we're just going to return y as the result. Let's see what the type of f is. So here the type of f is give me an alpha, and then I'll give you a function from alphas to alphas. If I write the same thing, but without any type annotations, then the x and the y are completely independent. So let's call this g, and look at the type of g. It says you give me an alpha, and then I give you a function from betas to betas. What this means is that beta doesn't have to be the same as alpha. But in f, they do have to be the same, and again, that's because I wrote the declaration here. The quote a, as soon as you use quote a within some binding form, its meaning extends for the entire body of that binding form.